You can't hear light and you cannot see sound, and yet, thanks to modern microcontrollers and digital electronics, we're able to visualize sound in real time in some very fascinating ways. Join me today for the sound of LEDs, and along the way, I'll even tell you what a boustrophodon is and why it matters. Hey, I'm Dave. Welcome to my shop. In a recent video, I covered the history of LEDs and how they work. You might remember our friend the electron and his spontaneous photon emissions.
Oh, that's better.
We also covered how the individually addressable LED works. I'll put a link to that video in this video's description. And today, we're going to use that technology to visualize sound waves in real time. We'll even go one step further into live musical analysis and try to respond to the beat of the music in some intelligent way as well. As frequent viewers of the channel likely know, I've got autism. And while being overstimulated by the auditory and tactile senses can sometimes be overwhelming, I have an enormous appetite for bright primary colors. Here's the very first album I ever bought, based entirely on its cover at the time, very RGB. My favorite toy was the light bright, and here's what my shop today currently looks like. As you can see, I spend most of my days sitting in a big shop filled with thousands of brightly colored LEDs. It turns out that I've got an eidetic memory for visual input and almost no memory for anything my wife tells me to remember, unless it's on a whiteboard or a fridge where I can actually see it. Just as certain sounds can be music to the auditory senses, some of the visualizations I'll show you today are much like music for the visual mind. Now, the most basic audio visualization that pretty much everyone will be familiar with already is the classic VU meter. Now, I suppose everybody has seen one, and most are familiar with the name VU meter, but it seems only a few folks actually know what VU stands for. Volume unit. These meters go as far back as the 1940s, when the physical characteristics of the meter itself helped define how a VU meter should act for decades. For example, the standard was to use a 200 microamp ammeter fed from a full wave rectifier. I thought saying that would make that dude appear or something. Perhaps it has to be a full bridge rectifier before.
Full bridge rectifier!
There we go. I am pretty sure that the difference is that the full wave rectifier only grabs the positive part of the waveform, whereas the full bridge rectifier reflects the negative wave and grabs that too, and so it's more efficient and makes more voltage. No wonder he's so excited about them. The meter itself should use a fairly heavily weighted needle so as to smooth out the peaks. The level specification says this should be calibrated with a 1000 Hz test tone. Here's an example of a pair of analog VU meters from my Pioneer RT707 reel-to-reel. And for comparison, here are the digital examples from my Pioneer RT909 of a few years later. Now, the most natural way to represent volume units with LEDs is to make a bar graph, just like the 909. When the bar graph is empty, that's no sound. About 3/4 of the way up can be found 0 decibels, which is, for traditional devices, the maximum amount of signal that can be passed without clipping the tips of the waveforms off, which is a type of distortion. When that graph is full, that means the signal is completely saturated and already somewhere past clipping distortion. Normally, VU meters continue up to +3 or +6 decibels, so you can have a little more range to work with. Certain types of tapes, like chrome and metal oxide, can also be overdriven a bit past the traditional 0 dB, but we won't worry about that aspect for today. On a mechanical meter, 0 decibels would be 1.228 volts, which would push about 2.5 watts across a 600 ohm load. Every mixing engineer has their own preferences, but traditionally, they would aim for something like -14 dB of average volume. Basically, the higher your average volume, the better your signal-to-noise ratio, but the more room you leave up top, the more room there is for dynamics in the music. To make even the simplest VU meter then, we need to know how to use a microphone to measure the sound levels, how to get those levels into a digital device that controls LEDs somehow, and then to be able to draw the levels that we measured onto the LED bar graph. Let's have a look at a basic LED VU meter. In this particular implementation, the meter actually measures mono sound levels and then mirrors that display to look like it's doing stereo, but both sides are drawn identically, so we only need to look at the one side. Now, I'm going to be using an ESP32 microcontroller to build our little VU meter along with some LEDs. The ESP32 has built-in analog to digital converters, and the module we'll be using has a microphone accessory connected internally to one of the pins. We set the chip up to record a burst of samples from that input pin at 44 kHz, the same rate as CD audio, and we let it rip. To grab the samples into our code, we will use I2S, a serial protocol where the results are delivered by DMA, or direct memory access. Let's talk about DMA for just a second, because it's kind of important here. Let's say we want the chip to collect 1,000 audio samples for us. If we did it old school and just looped while looking at the pin, that would work, but your CPU would be fully busy all the time that you were sampling the audio. With I2S and DMA, all we need to do is to tell the microphone module to go and grab 1,000 audio samples and put them in memory somewhere for me, and then raise and interrupt when you're done so that I know they're ready to use. And that runs completely async to your CPU. When that interrupt finally happens, we have a little buffer with 1,000 1-byte audio samples just sitting there ready for us to work with. And the CPU was free to do other things that whole time. The values that come back depend on the analog to digital converter and how it was set up and how many bits and so on, but for our purposes, every sample is going to be a byte value from 0 to 255 that indicates overall audio loudness. As you might have guessed, 0 is no sound and 255 is the maximum that the microphone can sense. We're trying to draw a VU meter, so we need to know how many of its LEDs to light up at this moment, which is to say what ratio of its LEDs should be lit versus unlit, all of which is based on the VU value of the audio samples that we just collected. But do we look at the highest value from the whole set and call that a peak, or should we average the values out? Opinions vary, but in my own implementations, I always take the average. I suspect median would be even better, but you would have to sort your data. To get it, I add up all the audio samples and then divide by the number of samples, and that's my instantaneous average audio level value. Now that we know how loud the audio is, we just need to know a few more things like what color to draw the LEDs in, and of course, how to draw an LED. Our display is going to be a 48 by 16 LED matrix, and the VU meter will use the top row of pixels. Since it's fake stereo, as I mentioned, and really only using half the display, our VU meter will actually be 24 pixels wide on each side, and we'll just mirror it. As an example, if the audio levels are half of the maximum, then we need to draw 12 pixels on the graph for that frame. To figure out the color, I will simply do a palette blend of green, green, yellow, and red, and the further out I draw from the center, the further I will go into that blend. Like a great many traditional VU meters then, it'll be green at low values, yellow at moderate values, and then red up at maximum. As you can see, this meter adds one extra complication, that is peak tracking. When the VU meter reaches a new local maximum, it keeps those LEDs held active for a few seconds and then records where that peak happened and when, and then those LEDs fade out to black. To accomplish that, our bar drawing code will always keep track of the highest value that it's seen, and it starts a millisecond timer when it first sees that value. Our code is written such that the amount of fade out is based on how long it's been since that peak occurred. After 1 second, if it's not been bested by an even higher level, the peak is then reset to 0. There's just one matter we have to discuss. How do you go from a string of LEDs to a 2D matrix of them? For example, the visualizations we will investigate today will use 3 16 by 16 LED panels so that I wind up with that previously mentioned 48 by 16 matrix. But what's the difference between an LED matrix and an LED strip? Well, it turns out surprisingly little. In fact, one of these 16 by 16 matrix panels is really just an LED strip woven up and down across the surface of the matrix. That path or shape is essentially the same way a farmer would plow a field, right? And that's why it's known as a boustrophodon, which is fancy Greek for as an ox turns while plowing. Now you know. It's also how most people do their grocery shopping too, I suppose, so maybe next time you're at Costco with your wife, you can drop a little boustrophodon reference. But if she knows the Greek and busts you on it, remember that it's you that called her an ox and not me. Now, each panel has an input connector where we connect the signal wire as well as power and ground. Thanks to the manner in which individually addressable LEDs work, we can just plug another panel's input into the final output of any other panel. Not only will it grab power and ground through its connector, but it will also add the LEDs to the end of the chain. So if there are 256 LEDs in that first 16 by 16 panel, then the top left LED of the second panel is just LED number 257 in the chain. If we then hook 3 of them together in series, we just get a longer field for that ox to plow. And the problem is when we want to draw to that matrix, we're going to want to do it with X and Y coordinates, but that's clearly not how it's laid out. We need to be able to take those X and Y coordinates and then figure out precisely where on the internal strip the LED lives that represents our 2D pixel. Let's consider it this way for a moment. It wouldn't be an efficient way to wire it, but let's say the columns always ran from top to bottom somehow. Then, to get the strip index of an XY pair, all we would need to do is to multiply the X coordinate by the height, which gives us the start of the column where it lives, and then add the Y coordinate in that last column. And we found it. Well, the reality is that this is already the case for all the even columns. Looking at our boustrophodon again, it's clear that only the odd columns are reversed numerically, and that's the key. If we simply reverse the Y coordinate when referring to an odd column, that's pretty much the entire algorithm. To put it in a way that might be easier to grok, we multiply the x-coordinate by the height to figure out where the column starts, and then, if it's an odd column, we count off our y-coordinate from bottom up. Otherwise, we count them off from top down. And that simple approach lands us at the right LED every time. Now, for the nerds in the audience, let's take a quick peek at the code that does that. It's a simple function called xy that takes, you guessed it, the x and y coordinates and returns an LED index on the strip. The first thing it does is check the x-coordinate to see if it's odd. If it is, then it's going to use the reverse of the y-coordinate, which it does by subtracting the y-coordinate from the height of that column. For the even rows, it simply gets the column start by multiplying and then adding the y-coordinate. Thankfully, that bit of magic is already built into the code project I'll be using, known as Night Driver Strip. From simple animations to rendering large video walls over Wi-Fi, it can do most everything you need when it comes to individually addressable LEDs. Of course, I'm fairly partial to it because I wrote it, but you don't need to know anything about it unless you want to build these projects for yourself. And if that's the case, check out the video description for more information on how to do so, and be sure to get subscribed to the channel for a lot more info. Our next big visualizations will be created by taking those samples that we just acquired for the VU meter and then sending them through a fast Fourier transform to perform a spectral analysis on the audio and to break the music into 12 bands that correspond to those you'd find on a stereo equalizer. Now, if that sounds like a lot of word salad, let me try it another way. What if, instead of only one VU meter for overall loudness, we had three? One showed the loudness of the bass portion of the music, and the next one showed the loudness of the mid-range, and then the final showed the loudness of the treble. And that's what we're going to do, except we're going to do it with 12 bands. When we display those bands on the LEDs as a series of stacked VU meters from left to right, it will create an audio spectrum analyzer for us. To show it in action, I'll run a test tone sweep from 20 Hz up to 20 kHz, and we'll see how that sound moves up through the audio spectrum on the display. It starts down in the leftmost band around 20 Hz, and then it moves to the right as I increase the frequency. Now, note that I didn't even bother hand-waving over how this is done. I just said fast Fourier transform, like we all know what that is and how to code one if we needed one. Well, I'm not a math geek, so here's how I like to imagine that it works. You've got a stopwatch, but a really fast one. It only has one hand, and that hand goes around like 20 times a second at its slowest and 20,000 times a second at its fastest. So you start at the low 20 Hz. And instead of taking our 1,000 audio samples all at once, we'll take a sample every time that second hand is pointing up. You compute the view and call that the 20 Hz band. Next, we speed the hand up to 40 Hz, and we take a sample every time it's pointing up. The VU we find from those samples is our 40 Hz band. And so we keep speeding up the second hand and taking new samples on a periodic basis like that. It's kind of like that, and what the fast Fourier transform algorithm does is to give you a way to do all that work mathematically without stopwatches and repeated resampling. Instead, we just take the 1,000 samples just like before and hand them off to the FFT function. It comes back with those samples nice and tightly packed into 500 buckets of frequency information for us. All we have to do is combine those down to like 12 reasonable bands by combining the peaks, and we're ready to draw. Now, the FFT algorithm uses cosine and sine to determine how closely aligned any particular sample is with any particular frequency. Those that perfectly align with the clock hand are fully represented in the output, while those that are simply near the frequency contribute only a little bit. I was going to make an attempt to really explain how fast Fourier transforms work, but the reality is that we could spend the entire video on it, and I'm still not sure there would be enough time. So I'll put a link to a good 3 blue, 1 brown video in the description if you're desperate to get jiggy with the graphs and symbols, but for my purposes, it's really only important that you know what it does and not how it does it. In the end, for me, it's like 3 lines of code in a library because I'm not going to write a full FFT from scratch when there's already a dozen that have been debugged to choose from out in the open source world anyway. So regardless of how it does it, we give it our 1,000 samples and it gives us back 500 buckets. Each bucket corresponds to how loud the audio was at each little frequency band. If we're covering 20,000 Hz of range and there are 500 buckets, then every bucket covers a span of 40 Hz. At higher frequencies, we need much wider bands. It's actually a logarithmic growth in size from one band to the next. Take a look at an audio equalizer as an example, and you'll see that the bottom bands might only be 20 Hz apart, but they are thousands of Hz apart up in the treble range because the frequency values up there are so much higher. So to reiterate, here's what's happening. We tell the microphone module to go and collect 1,000 audio samples and deposit them somewhere in memory for us using DMA. We then hand those 1,000 samples off to the fast Fourier transform routine, which does the analysis and returns a set of frequency bands. We then group those into about 12 logarithmic bands and display a VU bar for each of them. And that gives us a nice spectrum analyzer. Now, the last thing I'd like to look at today is beat detection, whereby we do some processing on the audio to determine if and when a sudden beat has occurred in the music, and then we take some specified action like lighting up a part of our light organ. To make it work, all we really need is a constant stream of current VU values, and we'll figure it out from there. We're going to watch for a major change in the VU. The code makes use of a value known as the VU ratio, which I calculate as how low the volume is or high compared with a running weighted average. At 1.0, that means it's average, and the value can range from 0 up to 2. You could do a very trivial beat detection scheme simply by watching for the VU ratio to cross from below 1 to above 1, since that would mean it's going from less than average to more than average. But that's not quite precise enough, so what I wound up doing was latching or arming the beat detection when the average went somewhere below a threshold like 0.5. And then, if the VU ever crosses above 1.75 or some other metric I pick, after having been latched down low, I call that a beat. In this little code snippet, we can see that there's an onBeat virtual function. In C++, you would derive your effect from this class, and then your effect would implement whatever it wanted to do to react to a beat in its own onBeat function. Below that, we can see the latch being set when the VU ratio goes below 0.5 and then triggered when it goes above 1.75. Here's an example of that code running on a set of 5 glass insulators. When there's a beat, one of the insulators is randomly lit and then it fades out over the course of a second or two. There are literally dozens of similar effects defined in the Night Driver codebase already, and implementing new ones is incredibly easy. If you're interested in building on any of those projects for yourself, please check out the Dave's Garage Discord server linked in the video description, or go directly to nightdriverled.com to check out the actual code. If you have any interest in matters related to autism, Asperger's, or ASD, please check out my book on Amazon, Secrets of the Autistic Millionaire. Now, it's got nothing to do with money and everything to do with living a successful life on the spectrum. It's everything I know now that I wish I'd known back then. Remember, I'm mostly in this for the subs and likes, so please be sure to leave me one of each before you go today. In the meantime and in between time, I hope to see you next time, right here in Dave's Garage.